So thank you very much for the introduction. It's a pleasure to talk here. Also, I would like to thank the organizers for setting this up. I think it's a great initiative to do this online. And yeah, so my talk today, I gave it the title Overparametrization and the bias-variance dilemma, or I could also have called it maybe to which extent is this a bias-variance trade-off a universal phenomenon that holds for all methods, and to which extent can it maybe in an overparametrized regime could it be beaten by modern machine learning? This is the question that we started with, and I did this project together with a postdoc, Alexis de Rumigny, and he's with us in the Netherlands. And we also published something on RKF about 2 months ago. So if you want to know all the details, please look this up. Or you're also always welcome to ask questions also during the talk. You see, I just have 13 slides, and I hope that we can somehow, yeah, that makes it more enjoyable. Maybe if we have some sort of interaction during the presentation. So let me go to something which also Stefan was already alluding to, this double descent phenomenon. This is quite striking, something which really puzzled me when I first heard about it. And so, as you know, of course, we all teach these classes where we, in the textbooks, explain the bias-variance trade-off, and it works as follows. So we take a method, say a neural network or any other method that is somehow indexed by a number of parameters, and then we have the choice, for instance, in terms of the architecture, how many parameters we include. And if we take very few parameters and look at the generalization error, then we are here in this regime where we make a big mistake because we are not flexible enough with our method. Then with this bias-variance trade-off tells us if we include more and more parameters, somehow we improve because the method that we use has more degrees of freedom, so it gives us more flexibility. And then we reach at some point some sweet spot, and afterwards the generalization error will increase again, because we start to fit the noise and we start to overparameterize. And this is where the books typically stop here. And then you can wonder what happens if we continue adding more and more parameters. Well, most people would say, well, it goes on like this, or other people might think, well, it might stabilize at some point or whatever. It doesn't matter, because it's anyways very, very far off from a low generalization error, so we don't care about this. And all of this is not true. What happens for this modern machine learning thing is what you can see on the right-hand side. This is a real plot for, I think we did it for this random Fourier model. And so what you see in the first part of this plot, if you increase the number of parameters in this model, so you get exactly this U-shaped curve as before. And then instead of going up or stabilizing, it really has the second descent. So it goes down a second time, and reaches somehow for very large parameter values, number of parameters, it gets to small values. And so this is this new modern machine learning regime where most people believe, somehow for instance, these highly overparameterized neural networks are in this modern regime, and we should understand why does it work here. So the general belief is that here the methods that we use, for instance, the stochastic gradient descent, they have themselves a regularizing mechanism in the sense that they try to somehow find an interpolating solution that minimizes the overall L2 type norms of the parameters, and that itself has some sort of regularizing mechanism that forces the solution to be not some sort of interpolation, but a sort of a smooth type of interpolation, and that is already enough in order to bring the error down. So and then this is clear. I mean, this happens in practice, and that can be observed in many applications and for many different machine learning methods. And then there are quite a number of rather wide claims that in this overparameterized regime we could have, for instance, completely different statistical properties than in the original regime. Okay, so and here this is for the neural networks. There's a very influential article from '92 where they study all sorts of statistical properties of neural networks. And in this paper, they say, well, also for neural networks, the bias variance trade-off has to hold. Okay, so they can't beat the bias variance trade-off. It's the same for all methods. They say somehow it is universal. But then if you look, yeah, so these, I just mentioned here 2 articles. One of them was also mentioned in the previous talk by Stefan, namely the article by Misha Bekin and co-authors. And all of them have something, yeah, on bias variance trade-off in the title, because there's a bit this idea, well, in this overparametrized regime, there's maybe something new going on, something which we cannot observe with any of the classical methods. Okay, so this is really the question that we started with, is the bias variance trade-off, does it still hold also in the overparametrized regime, maybe in a different form, or is there some, yeah, just something new going on here? And what is interesting is in mathematical statistics, we have been working on lower bounds for estimation rates for a long time, but no one really has studied this yet in detail, whether also, for instance, the bias variance trade-off, whether there's a sort of lower bound for the bias variance trade-off. And so this is, yeah, the thing we need to do. We need to come up with a sort of lower bounds and see, look, what can we prove on what is necessary in order, and which has to be satisfied for all existing methods. Yeah, so this is exactly what I was just talking about. So this framework of minimax lower bounds, where we link the problem to some sort of information theoretic quantities and the idea of hypothesis testing, and then we can show, for instance, for certain methods that a certain rate cannot be improved more than, yeah, given rate. And something like this, we would like to do that for this bias variance trade-off as well. So what can we do if we have such a low amount? Well, we can answer certain questions. For instance, we can answer whether in the overparametrized regime the bias can be, for instance, much smaller than the variance, and maybe the rate is completely driven by the variance, but the bias is much smaller. That would have, from a statistical point, many attractive properties, such an estimator, because the bias causes a lot of problems. For instance, if we want to do uncertainty quantification or confidence intervals, so we always have to somehow come up first with an idea of what the bias is to center the estimator. And another thing is we want lower bounds for this U-shaped curve. Okay, so maybe I can go back to this plot. So what we want is, we want somehow a method that tells us that, well, there's no method that can do better than maybe this. Okay, and all what we have at the moment is essentially with this minimax lower bounds, we have a global lower bound which tells us that no method can cross this global lower bound, because that would be better than a minimax estimator, and that can't be true. Okay, so we want really something where, if we can say we restrict ourselves to methods that have maybe much smaller bias, then we have to accept that the generalization error is suboptimal in a certain sense, and that would generate this U-shaped curve. Okay, so I hope the motivation is clear. So there is, if I say it hasn't been studied at all, this is not entirely true, because there are 2 papers, and the first one is by Mark Lowe in the Annals of Statistics, and it completely characterizes somehow this bias variance trade-off phenomenon in what we call the Gaussian white noise model, which is somehow a bit an analog, a continuous analog of the standard regression setup that we always study in machine learning, and looks at it for functionals. Okay, so it studies functionals and can, because of some sort of worst case thing, can reduce that to a one-dimensional problem. And for this one-dimensional problem, one can then use something from the parametric statistics in order to analyze the bias variance straight off in this parametric setup, and then one can work it out. But this is not extendable to, say, a wide range of problems, and also not to problems that are not functional. So that is a bit limited. And then there's another paper by Panzagel in 99, also already quite a time ago. And there it is shown somehow that if you have some sort of unbiasedness property of your non-parametric estimator, that would force the variance to increase. And that is also done for functionals, but in a more general setup than in the paper by Mark Lowe. And since then, I think we searched the literature, and there was essentially no work anymore continuing on these ideas. And the missing piece here, I think, is really this sort of general treatment of how to derive lower bounds for the bias variance trade-off. Now let me show you the main idea. This is essentially, it's very basic. This is what is used also in this work by Mark Lowe. And it goes by something which we all know, the so-called Cramer-Rao inequality, or Cramer-Rao lower bound. And the Cramer-Rao lower bound tells us that for any estimator, if we say we denote the variance by V, then this variance is, or this V is lower bounded by an expression which is 1 plus the derivative of the bias, and the derivative here with respect to the parameter, and this squared divided by the Fisher information. The Fisher information is just something which is somehow generic to the underlying model. And so if we have with this bound, we can derive, in principle, for parametric problems, you can derive lower bounds on the bias variance trade-off. How does it work? Maybe I just show it. So if the bias is small, okay. So what does that imply? It implies somehow so here's the true thing, the true theta, and then so the bias always has to stay close to this, or the bias has always to be in a small band around 0, so it cannot escape this band. So that means that essentially there exists a theta star such that the B prime of theta star is larger than -1/2. Say, okay, so the -1/2 is a bit arbitrary. So if there would be no such theta star, then it somehow the bias would escape, and the bias would become large at some point. Okay, so that therefore there has to be such a theta star, and that implies then, well, with this Cramer-Rao lower bound, this implies that for theta star the variance is lower bounded by 1/4, say, because of this -1/2 f theta star. Okay, so and that gives us then a lower bound on the variance. And so this is a very basic idea, but of course it's limited somehow to parametric problems. Okay, so it's because it needs the Fisher information, and the Fisher information requires something differentiability with respect to the parameter. And yeah, so it's not clear what a non-parametric. I mean, people have tried it for functions, for instance, but in general, it's not really clear what Fisher information is in a complex non-parametric or high-dimensional problem. Now, okay, so this is the thing we have to overcome. We have somehow to deviate away from this Cramer-Rao inequality. And if we now think again, like these lower bounds that we do for the minimax estimation risk, and they are based on these information in quantities such as the Kubat-Leibler, total variation, chi-square distance. And that is exactly what we want to do. Somehow we want to find something, inequality that has a bit the same properties as the Cramer-Rao lower bound, but it should somehow be based on things that are generic and that can be done for all models. And that is what we have been working on. This is somehow the abstract framework, and then based on that one can derive a lot of problems. Maybe let me go through this a bit, explain it. So it's yeah, quite abstract. We just say we have a number of probability measures that are defined on the same probability space. So we say from P0 to Pm. And then we define a matrix that we call the chi-square divergence matrix. Why do we call it like this? Because essentially on the main diagonal you have the chi-square divergences, and on the off diagonal you have some other entries which are given by this expression here. So this is just a matrix, and it's somehow, yeah, completely computable for any complex model whenever we can evaluate or estimate the chi-square divergence, which is the case for many, many non-parametric and high-dimensional models. And then and now this holds really for any random variable x. We can define this vector delta, say, and the vector delta is just the difference of this of the random variable x, of the expectation of that, with respect to the different probability measures. Okay, so we take p0 and then we look at what is the expectation for under different probability measures. So therefore we call this change of expectation. So we change from one distribution to another distribution that changes the expectation, and here in this delta we look essentially how these expectations change. And then we have this inequality here, and that tells us that the variance and under p0 of this random variable x is lower bounded by this quadratic form where we take the inverse of the chi-square divergence matrix. So in general, it could be, for instance, it could be pseudo inverse if it's not completely invertible, but maybe we don't care here for this exposition. And we also have this the deltas here. Okay, so what I claim here is this is essentially a sort of, it has exactly the same flavor as the Krammer-Rao lower bound. Actually, you can take a limit and you come back to the Krammer-Rao lower bound, but it has this advantage that it does not require the Fisher information. It can be also applied to complex and high-dimensional and non-parametric models. So why is that the case? Because we will, for x, we will take, for instance, an estimator theta hat, yeah, and then because it holds for any x, we have a lower bound for all the estimators theta hat. And if we take a theta hat, then we have here the difference of these expectations. And if we know that the bias is small, then the difference of the expectations should be also linked to the difference of the parameters. Okay, so just triangle inequality, and then we have if we take these probability measures in the right way, we can somehow make the difference between the parameters in such a way that we got a good lower bound for the variance. Okay, so that is the ingredient that we now have to do in order to derive lower bounds for the bias-variance trade-off. Okay, let me continue here. Now, this is all, and now I just give you some examples to show you two things. First of all, I want to show you that it can be applied and can give good lower bounds for a wide range of models. And the second thing that I want to highlight here is that for different models, there could be different bias-variance trade-offs. Okay, so it's not exactly defined what the bias-variance trade-off is. And you will see in a moment that, that there can be quite a lot of differences in the formulation, and there are some weaker ones and some stronger ones. So we start with again with this Gaussian white noise model, which theory people really prefer compared to this regression model because we don't have all these discretization effects, but it's essentially the same. Okay, so we do this because it leads to much neater analysis. And then what we want to do is we want to estimate the function, this regression function here. We want to estimate it at a fixed point, say x0, say a half or something like that. And we assume that the underlying function is beta smooth, and beta is here in the Hölder sense. This is very standard in this non-parametric regression literature. And then what we can prove is this lower bound on the bias-variance trade-off. It says that for any method, whatever you take, whether you take a neural network or you take classical kernel smoothing or whatever, it's for any estimator, for any reconstruction or learner or so, we have the following. So if we take the worst case bias over the parameter space, we take it to the power 1 over beta, where beta is the smoothness of the function. We multiply it with the worst case variance over this function space, then this has to be always lower bounded by 1 over n. Okay, so why is that now a lower bound on the bias-variance trade-off? Because essentially it says if we have a small bias, we must have a large variance. So if we have a small variance, we must have a large bias. Okay, so and it really, if you would plot it, it really leads to this sort of U-shaped phenomenon that we have seen before. So that really says in this setup, there's nothing we can do. It's just it's a universal limitation of any method that has to satisfy that. If we want a method which is more biased, we have to pay a large variance, which makes the overall generalization error suboptimal by the bias variance decomposition of the mean squared error. And okay, so now you can wonder that sharp. Yeah, so we know many methods in non-parametric statistics that also intend an upper bound that is of the order 1 over n. Okay, so then you see it's really matching. So typically, if you take an estimator, you have a bias which is, you have a smoothing parameter h, and then you have a bias which is of order h to the beta, and you have a variance which is of the order 1 over nh. And now you see if you take the bias to the power 1 over beta, so you get an h, and then you multiply with 1 over nh, so you get a 1 over n. So that means really we have matching lower and upper bounds. Now you can wonder here, what about the soup? Okay, so we have a soup in front of the bias, we have a soup in front of the variance. That really means only in the worst case sense. Yeah, so there's only one parameter and they don't need to be the same. Okay, so there could be one parameter with a large variance and the one parameter with a large bias. Can we do something stronger here? We would like to have it that it holds for all parameters. Is that true? Well, we also have a condition that says essentially, if we are in this part of the, okay, if we are here in this part of the U-shaped curve, where we have a bias that is optimal in a sense, or smaller than optimal, then we can also replace the variance by an int. And we also know that we never can replace the soup in front of the bias by an int. It's just not true. Okay, so there are methods that on a large subspace of the parameter space can also have a smaller bias. It's just in the worst case sense here. Good. Okay, so that's also essentially the thing in this specific setup. Now you're probably saying, okay, so it has nothing to do with this modern machine learning because that is in high dimensions. Exactly the same question that we also asked. So we wanted to apply this framework to a high dimensional model. So we took the simplest high dimensional model that one can imagine, namely the Gaussian sequence model, where we observed just n copies of x1 to xn, and the xi is just a normal with the unknown mean theta I and has a variance 1. Okay, so there are n parameters and n observations. And then we look at sparse signals. Okay, so we want to say the vectors are S sparse, and here we have to restrict to S to be smaller or equal than something like square root of n. It's not very important. So what is the bias variance decomposition in this case? Well, if we take the overall risk in this model, then we can decompose it into a bias and the variance part, and the variance part is the sum of the individual variances. The bias part is somehow this L2 norm between the expectation and the true vector theta. And so it's well known that in this model, the optimal rate is actually, so the optimal rate is this. Okay, so it's for estimation of the vector theta, that is in terms of the sparsity, and then times the log factor that comes because of the searching thing. And so what we are interested in now is what happens if we decrease the bias, make it a bit smaller than the optimal rate, and how we model the decrease is by this constant gamma here in front, and then we wonder, so what does that imply in terms of the variance? And what you can see here is this bias variance lower bound that we have tells us that the variance part here is in this case lower bounded by a term which is n times something which depends on this gamma. So it's a 4 gamma. So that means even if we make this constant in terms of the bias small, so we don't make the bias actually of a smaller order, or so we just make the constant in front of the bias smaller, that already makes this gamma small, which then appears in the exponent, and it will force the variance at 0. So this is So it's not the soup over the variance, it's the variance over one specific parameter, namely the zero parameter, but you could have done it for many other parameters as well. And it will force it to be of the order n, which is highly suboptimal. Okay, so if you compare this rate, with the rate n, then if for instance s is, I don't know, n to the 1/4 or so, then this is of course much smaller than the n. So what does all this tell us? It tells us essentially that in this case here, the bias variance trade-off is much more extreme than the one in this Gaussian white mouse model that I considered before. Yeah, so it's actually not a U-shaped thing in this high dimension setup. It's sort of a phase transition. Okay, so you go down with your bias, you immediately go up with your variance. There's nothing you can do against that. Okay, so it's also much stronger because it does not require a soup in front of the variance. You really have it for one parameter here. And you also, we also have extended it to the high dimensional linear regression setup. Now, my time is almost up. Just for the last 2-3 minutes, I just want to show you some other setups for the machine learning. I think the most relevant one is the Gaussian white noise model, which is regression. And then it's before we looked at the pointwise estimation. Here we look at essentially the prediction error, if you like. Okay, so we study the prediction error, and the prediction error has also a bias variance trade-off decomposition. So this is the prediction error, and can be written in a squared integrated bias plus an integrated variance. Okay, so and then we can wonder, is there also a bias variance trade-off for these integrated quantities here? And this is a hard problem already for the minimax lower bound. So for minimax lower bounds, which is a weaker concept in a sense, we know that for this specific loss function, deriving lower bounds is quite complicated. It relies on some very difficult counting arguments, some sort of combinatorical things that make it quite nasty to prove such a lower bound. So that also turned out for the bias variance trade-off turned out to be a very hard problem. And here just applying this inequality, this change of expectation inequality that I have shown you before is not enough. So you need to do a bit more work here. And what we do here is we somehow combine it with this, what we call reduction techniques. Okay, so first we show that if the bias variance trade-off in this model for this prediction error, that can be somehow linked to the bias variance trade-off in a different model, which is again some sort of sequence model. And also we can show that we can reduce it to a smaller class of estimators. Okay, so we can just look at a smaller class of estimators that have somehow a certain symmetry property. And we know that for all the other ones, the bias variance trade-off is not going to work anyways. So once we can reduce it to these two things, we can afterwards then apply this change of expectation inequality and derive in a few lines argument, we can derive a lower bound. And here's the lower bound. You see it's essentially of the same type as in the pointwise case. We get if we put the bias to the power 1 over beta, with beta here the Sobolev smoothness. And if we multiply it then with the worst case integrated variance, we get also the lower bound of 1 over n. And it's matching with the upper bounds for many methods that we have, which also would have for exactly this quantity an upper bound of 1 over n. So there's no gap here. And then just to finish, so you can wonder, is that now something very tied to bias variance trade-off? There are many different concepts in the literature, also for classification and so on, where people propose variations of the bias variance trade-off. And here I think the most natural one is if you look instead of the trade-off between the bias and the mean absolute deviation. And the mean absolute deviation is just given here in this one. As it's just essentially how the estimator spreads around. It's either a mean or median. And so this is actually a bit harder to derive such change of expectation inequalities. We managed it, but it's not fully developed yet. I think that would be something for future work. But in principle, I think one can do something similar, and these sort of universal lower bounds, they are still true. So just to summarize, and then I'm done, is what we did is we came up with somehow a general framework because we are interested in to which extent is this bias-variance trade-off universal, and we derived a framework, and it allows us to derive for a number of models. There are more actually in the paper. I didn't mention all of them. For a number of models, that allows us to derive lower bounds in the bias-variance trade-off that match also the known upper bounds for many methods. We can see that different types of bias-variance trade-off, sometimes they're just in this sort of worst case phenomenon, worst case scenario where we have just a soup over the parameters, and sometimes we can also take the int, and sometimes we can take specific parameters. And so that makes a huge difference actually in the interpretation of what it is. But the overall message is the bias-variance trade-off is universal. So there is nothing you can do with whatever method, whatever you do in overparametrization. Also, you cannot beat it in exactly the way as it's stated in the results. Okay, so if you're interested in more details, and so then you can look up the article or just ask a question. Thank you very much.